Here we get to switch things up a little bit. So let's just kind of frame ourselves in the context that we've been working on. For the last while, I don't know, we've started with a function and we learned some derivative rules to find f prime of x. And then we learned a little bit about what that derivative was. We said, okay, this is the slope of a tangent line, the instantaneous rate of change of our original function f. From there, we could find the second derivative. And we began interpreting that. We said that's where the slope is changing. It's the rate of change of the derivative. And so really we have this idea of concavity that's going on. Our second derivative tells us about that. So we have these kind of step-by-step analysis things, and graphically we can figure out what's going on. Now we could go another step forward to our third derivative, and we could kind of keep going from there and keep analyzing things. But what I'm going to do is I'm going to take this original function, and we're going to go backwards, and we're going to say, maybe we could take a derivative of something to get this. I'll call this capital F of x, and we're going to call this an antiderivative. The antiderivative is just the backwards version of it. So we could say that this little f function is the antiderivative of f prime, because we go one step backwards to get there. And so forwards is derivative, backwards is antiderivative. And we'll connect this with something that we're going to call an indefinite integral, and that's going to build us up to some of the big ideas in calculus. But for now, we're just going to focus on trying to go backwards here, undoing our derivative rules, trying to see what function kind of came first. So this is our definition. An antiderivative of a function is when the derivative is equal to that thing. So again, capital F is the antiderivative of little f if capital F prime is equal to little f. So take a second and find antiderivatives for these. And what I mean by that is we're coming up with a function where these functions here are the derivatives of them individually. So whose derivative is 3x squared? What function's derivative is 8x plus 2? And what function's derivative is 1 over x minus e to the x? Take a second, pause the video, and see if you can come up with some of these. All right, so here's some options here. Capital F of x. My guess is that this one wasn't too bad. We said x cubed. This is the antiderivative, or an antiderivative, sorry, of this little f of x, because the derivative of x cubed is 3x squared. So if we go from capital F to little f, that's moving forward. We're saying we're finding a derivative. Here we're going to do the same thing, but we'll call it capital G now. Capital G of x is going to be 4x squared plus 2x. Notice you can check all your answers here. Just take a derivative. The derivative of this capital G function is going to be 8x. Sure enough, that's what we're supposed to get. Plus 2. And again, we're good. So finally then, we've got h of x, which is going to be, natural log of x minus e to the x. Cool. All right, here's your challenge. Do this again, but come up with a different function for each of these. So come up with a different antiderivative. Notice right here, it says capital F is an antiderivative. It could have said capital F is the antiderivative, but we didn't do that. We said it's an antiderivative. It's one of the antiderivatives. There are multiple answers here. Take a second, pause the video, see if you can come up with a different function for each of these, whose derivative still is going to be 3x squared, and then for the second one, 8x plus 2, and for the third one, 1 over x minus e to the x. Give that a shot. All right, by now you're probably either relatively frustrated or you're a little annoyed at how kind of easy that was, because what we'll find is that a different way of doing this is saying x cubed plus 7. The derivative of x cubed is 3x squared. The derivative of 7 is 0. And so for g of x, we could do the same thing. 4x squared plus 2x, let's say minus 9. Sure, that constant of negative 9 is just going to go away to 0 anyways. And finally, h of x could be the natural log of x minus e to the x plus half. all of these constants just end up going to 0, so it doesn't really matter what we put there. My guess is that if you figured this out, you used different constants than I did, but you could use any constant, which means really there's an infinite number of these antiderivative functions for each little f or little g or little h, because we can just add any number or subtract any number to the end, and technically we get a different answer, but it's still an antiderivative because the derivative of this thing is still going to be 3x squared. So that's something that's a little bit weird about antiderivatives. There's more than one answer. There's an infinite number of answers. We call these things antiderivative families, and so we're really going to just sum this up by saying plus c. This here stands for constant, meaning you can add or subtract any constant. C can be a negative to the end of this thing, and it'll still be an antiderivative. So all of the antiderivatives are the same thing up to some constant. So we're going to really focus on the function, but we're going to call this like the function family. And then at the end, we'll just say plus c. So if we go back, we could say, all right, all of these are the function families, the ones in green. And to make these antiderivatives, we'll just say plus c. There we go. So we'll tack that on every time to represent that whole antiderivative family. We could try and think graphically about this. Let me draw a quick set of axes, and we'll see what this looks like. And let me draw a function. And we're going to pretend that the function that I'm drawing is an antiderivative. Oof, that wasn't very good. Let me try that again. There we go. That's better. I don't know why, but whatever. Let's say that this is our antiderivative function, or one of them. Whenever we add a constant, what this does is it shifts our graph vertically. So we have a different picture that looks like that. Or maybe we've got one where we subtracted the constant and it shifts it down. And we have an infinite number of these that are infinitely close together because we just keep changing that constant. Now, these aren't perfect, but we're going to pretend that all of these graphs are the same. They're just shifted up or down. What you'll notice is that if we take any x value, if I cross it through here and I look at all the different points on the graph that touch this red line, right there, right there, right there, right there, and right there, if I've drawn these correctly, they all have the same derivative. So these functions that are shifted up or down all have the same derivative, or these are antiderivatives of the same function. So the slopes at all these points are the same. Now, it's not perfect in my picture because it's just not a very good picture. But if we're just shifting a function up or down, that doesn't change the slope. So these constants don't actually change the derivative of the function, meaning if we're trying to find a function whose derivative is this little f, all of these vertical shifts don't really impact anything. So we know the shape of the antiderivative, but we don't know exactly where it is because it could be shifted up or down vertically anywhere. But we know the shape of it. We know the actual kind of curvature based on the function family that it is. So that's kind of interesting, I think. This is the second part, indefinite integrals. Really, all this is notation. So if capital F of x is an antiderivative of little f of x, and again, here's that definition of an antiderivative. The derivative of an antiderivative is that function. Then we can write it this way. So this here is an integral sign. It looks like a really thin, straight S, which is not a coincidence. It stands for sum. You might see why later on, but we won't get into that too much. This is kind of like saying we're going to find the antiderivative of this stuff coming up. Sometimes I think of this as like an open parenthesis sign where it says, okay, start thinking about antiderivatives. This little f function we call the integrand. It's the function inside the integral. And dx is a differential. Now, it's going to mean a bunch of things, and it's a little bit difficult to explain what a differential does, what it exactly is. So I'm only going to give you what you need to know as you need it. For now, we're going to think of this as almost purely notation, and it's going to tell us two things. First, it's going to tell us end of the integral. So if this integral sign is the open parenthesis, this is the closed parenthesis. This is the period at the end of the sentence. This is the thing that says stop thinking about antiderivatives. Also, it's going to tell us that x is a variable. Maybe I'll put that down here. X is the variable. That's not going to be terribly important to us right now, but oh well. Capital F of x is the antiderivative family. And we get our plus c, which we call the constant of integration. All right, that's pretty messy, but oh well. So here's our same three antiderivative problems. They're just written with this integral notation now. And this is how we could do that. We could say the integral of 3x squared dx is equal to x cubed plus c. Because again, we said the antiderivative of 3x squared was x cubed. Similarly, the integral of 8x plus 2 dx is going to be 4x squared plus 2x plus c. The derivative of 4x squared is 8x, the derivative of 2x is 2, and then we throw in that constant of integration. The derivative of that is 0, so it doesn't matter. And here we've got a natural log of x. I changed something here, and I'll talk about it later. Plus c. I put some absolute values around that. Don't worry about it right now. But all of this notation part with the integral sign, it just acts in the exact same way as these questions. It's just framed differently. Here I said, find an antiderivative for these functions. And here I said, figure out these indefinite integrals. They represent the same thing, same question. We're just asking it in different ways. All right. Now we want to talk about antiderivative rules. If you've got that rules chart, feel free to start filling things in on there or just take some notes on it or whatever. But we're going to go through the same function types that we did when we were learning about derivative rules, and we're going to figure out how to undo our derivative rules for as many as we can. So the first one is the constant function. It might be easiest to start with an example. So again, what we're doing is we're trying to, maybe I'll type this so it's not so ugly when I write it. We're trying to come up with a function, oh my goodness, there we go, whose derivative is 3. And once we think about it this way, it's not too hard to come up with it. We're going to say, okay, the function whose derivative is 3 is 3x, and then of course we can add any constant plus c. That's going to be the same for any constant. For any constant, all we're going to be doing is adding that variable. So for any integral of k dx, that's going to be kx plus c. Done. For power functions, it's a little bit trickier. We're going to be looking at things like x cubed dx and x to the 5 dx. And I'm going to leave it here for now. Pause the video, see if you can come up with the functions whose derivatives are x cubed and then whose derivative is x to the 5. It might take a little bit of guess and check or trial and error, but try this out a couple times. All right, so the first thing you'll notice is that the exponents are going to go up now. If we had x to the 4 and we took a derivative of it, though, we'd get 4x cubed, and we only want x cubed, so we're going to divide by that coefficient as well. Now, we can check this by noticing the derivative of x to the 4 over 4 is equal to 4x cubed over 4, which is just x cubed, because now you can see, oh look, that coefficient that came out front cancels out with what we put in the denominator. So we end up dividing. Similarly, we've got x to the 6, but if we just took the derivative of x to the 6, we'd end up with 6x to the 5, and we only want x to the 5, so we divide by 6, and plus c on both of those things. So our rule is x to the n plus 1 over that number, plus c. Cool. So those are power functions. The reciprocal function is relatively easy except for one strange thing. For this one, well, two strange things, I guess. Sometimes these integrals will be written this way. you can think of this as multiplication and just bring that little dx out to the end. I always like looking at this version of it. I think it's a little bit easier to see what's going on. So if you see a dx up in the numerator, just tack it onto the end of your integral instead. That way it acts as that kind of closing end of the integral, end parentheses, period at the end of the sentence, that type of thing. So we know that the natural log's derivative is 1 over x, but before, you might remember that I threw these absolute values on here. Let's talk about why. When we talk about the derivative of the natural log of x, we say that that's 1 over x, but what we'll notice is that our natural log of x function just exists right here. And so when we talk about the derivative, we really think of this when x is greater than 0. Because the negative x values don't make any sense. We don't want to say, oh, at x equals -2, the slope is -half, because this function doesn't exist here, because the domain just goes from 0 to infinity. It only exists on the right side of the graph. Now we're going backwards. The domain of this is -infinity to 0, union 0 to infinity, or we'll just say x can't equal 0. So we want a way for this function to match that same domain as the thing that we started with. So the way that we do that is we put absolute values around here so that we don't have to worry about putting negatives inside of that natural log, because if we do end up with a negative inside of this, the absolute value will make it positive. I'm not going to be terribly picky about that, and in fact, a lot of people end up leaving it off later on when you get far into calculus. We kind of just assume that there's absolute values around the x when you need it to be, and there's not when you don't need it to be. But that can be a little bit tricky because you have to really focus on context, all that kind of stuff. So if you do this without the absolute values, I'll probably write it in on there, or at least remind you on the comments of the homework assignment if it's not on an exam or something like that. And then no points will be taken off. So it's not going to be a big deal. I'll just remind you. Anyways, let's think about the exponential function. This is probably the easiest one. What function do we need to take a derivative of to get e to the x? Well, e to the x, but you can add any constant. So those are all of our function types. Then we can deal with like sums and differences, and we'll talk about constant multiples and coefficients and stuff like that afterwards. For sums and differences, if we have two functions that are added together, sometimes I'll see it in this notation. I don't like this notation that much because it looks like multiplication. It's not. It's just f of x plus g of x. There's a couple of different ways that you can do this. Integrals, we say they preserve the sign, where you can say this is f of x dx plus the integral of g of x dx. And now the integral of f of x dx is capital F of x. It's the antiderivative. And this one is capital G of x plus c. Every now and then people think, well, wait, shouldn't there be another constant here? Maybe like plus c1 for the little one for this f of x and plus c2 for this antiderivative of g of x. Since both of those things are constants, we're just going to throw them out to the end anyways, combine them all together. It doesn't matter what they are, so we'll only use one. Also, we could go ahead and do the same thing for subtraction. So if we're subtracting those things, we just subtract. What does this mean? This means that in general, we can do exactly what we think we can do. If we're looking at the antiderivative of 18x cubed, we'll say, plus 1 over x. No, I don't want to do 18x cubed, sorry. Let me just do x cubed plus 1 over x dx. We can split this up into two integrals. X cubed dx plus the integral of 1 over x dx. And each of these have antiderivatives that we can do. We're going to do some power rule. So x to the 4 over 4. And this one's our natural log plus c. Now, in a lot of cases, we end up just going from this first step to the second step, but it's nice to notice that we can split up an integral based on addition or subtraction here. So this means that we can do polynomial functions and stuff like that pretty easily. For constant multiples, for these coefficients, they act a little bit differently. Essentially what happens is they can come right out. So it ends up looking something like this. So then we could say this integral here is really just that capital F. So we've got k times capital F of x plus c. Again, this means that things act exactly the way that we think. Now I'll do my 18x cubed dx. We could say that this is 18 times the integral of x cubed dx, and then it's 18 times x to the 4 over 4 plus c, which gives us 18x to the 4 over 4 plus c. 18 over 4 is really 9x to the 4 over 2 plus c. Now, I went ahead and I pulled that coefficient out, found the antiderivative, and then multiplied it in. Again, you'll notice I didn't really do the distributive property on 18 times c because it's just going to be some other number, some other constant. So we typically can just tack the constant on at the end. But now what we could do is just go directly here and say 18x to the 4 over 4 plus c. Keep the coefficient in our answers just like we're used to with the derivative. And from here, we can reduce the fraction again, get right back to that same answer. So really, it's the same rule as our derivative rule with those constant multiples. Coefficients just stick around in our answers. All right, so your turn. Use your notes, use those rules, flip back in the video if you want. But here's 4 functions. See if you can figure out what the antiderivatives of these things are. I'll give you a hint for, number 2, 3, and 4. It might help to rewrite things. All right, go for there. If you need a hint, I'll rewrite things for you. This one doesn't get rewritten, so I'll just leave that one. This one, though, we can rewrite. I'm going to rewrite this as 3 times 1 over x minus x to the half dx. That might help. And for this one, I'm going to rewrite as 4e to the x minus, this cube root is really an x to the 1/3, but notice it's in the denominator, x to the negative 1/3 dx. And for this one, I'm going to notice an upside down triangle. I'm going to split this thing up. I'm going to say this is 3x to the 5 over x, which is really 3x to the 4, minus 2 over x. But that's really, well, maybe I'll leave it like that. Anyways, if you haven't finished these, go for it now. All right, so let's see what our answers look like. Here, when we take our antiderivative, we're going to increase the exponent by 1 and divide by that number. So 7x to the 4 over 4 minus 4x squared over 2 plus, this one's, again, this constant, we're just going to tack on an x, so we get x plus c. You could rewrite this as 7x to the 4 over 4 minus 2x squared plus x plus c. Cool. There's that one. Maybe I'll put a little line here. For this one, you'll notice that we've got 3 times the natural log of x minus, now we're going to increase the exponent by 1. That's x to the 3 halves over that number, 3 halves plus c. Now, I'm going to, instead of dividing by this fraction, multiply by the reciprocal. So I'll say 3 natural log of x minus 2/3 x to the 3 halves plus c. For this one, we can pretty much just do the same thing. Let me separate that. There. Our antiderivative is going to be 4e to the x minus x to the negative 1/3 plus 1. That's going to be 2/3 over 2/3 plus c. So we've got 4e to the x minus 3x to the 2/3 over 2 plus c. That's that. It's a little hard to see. And lastly, we've got 3x to the 5 over 5 minus 2 natural log x plus c. Cool. These are all a little bit weird, but take a second, make sure you know how these are working out. There's lots more of these in the text to practice, so you'll get plenty of opportunity to practice your antiderivative rules. My guess is that these will come pretty quickly because we're good at derivatives by now, and so it won't be as hard to learn how to undo all those rules. There's one other thing we want to talk about in this video, and it's called an initial value problem. here's the setup. In general, our answers are antiderivative families. We've got this infinite number of vertically shifted functions. I'll draw the picture again just so you can see it. You've got all these functions. I don't know why I made that so wide. All these functions that are just going to be shifted versions of each other. Same shape, but we're just going to be moving them up and down. If we have more information, we're going to be able to narrow our answers down to a single version of this function, shifted up or down. All we have to know is a point. Once we know that point, we can say if we're supposed to have a graph going through there, oh my goodness, sorry, that sentence was terrible. If our antiderivative function's graph goes through that point, then I know the shape of it. It's going to follow the shape of all the others. But now, if it has to go through that point, I know exactly where it is. So an initial value problem, you're going to be given a point on the graph of your antiderivative. And you can use that to find out the specific antiderivative, a single antiderivative function. Let me show you what I mean. So we're going to find the antiderivative of this function here, but we're also going to be given this. So this is our initial value, we'll call this. The first half of this problem is going to act exactly the way that you'd think. We're going to say capital F of x is equal to the integral of 4x squared minus 2x plus 1 dx. If we want to find the antiderivative, we're going to use this integral stuff. The antiderivative of 4x squared is going to be 4x cubed over 3. The antiderivative of 2x is x squared, and the antiderivative of 1 is x plus c. So this is our capital F of x function. But now we have these two values. This is an x value, so we're going to plug it in here. And 2 is a y value, so we're going to plug it in there. So I've got 2 equals 4/3, if I plug 1 in here, minus 1 plus c, or 2 equals 4/3 plus c. Now I can solve for c. What that's going to be is 2 minus 4/3, or that's really 6/3 minus 4/3, so 2/3. What this gives me is that the single antiderivative function is still this 4x cubed over 3 minus x squared plus x, but now instead of plus c, I've just solved for what the specific constant of integration is given this. So I'm going to tack on a 2/3. That is the only antiderivative of this function who goes through this point. You could also say that this is a point 1, 2 on the graph. So that's how that's going to look. Isn't that kind of nice? So if you're given this extra bit of information, this initial value, you're going to end up with a single function without a plus c, not the big family of functions anymore. And that's really the only time that we end up with these when we're dealing with these indefinite integrals, if you're given that extra bit of information. So here we'll do the same thing. Maybe I'll let you figure this part out and think about what this overhead fixed cost is. Try that. All right, if you're looking for a hint, that overhead fixed cost, and if you're not looking for the hint, just pause the video until you're done. The overhead fixed cost thing means that's the cost of producing nothing. So that's when x is 0. So we're going to use that. All right, if that's all you needed, pause it, finish it out. If not, here we go. We want capital C, and we have the derivative. So what we want to notice is that capital C is the antiderivative of marginal cost. So that's the integral of 0.3x squared plus 2x dx. That means our cost function is really going to be 0.3x cubed over 3 plus x squared. I'm going to say plus k now. The reason I'm not using c for my constant of integration is that c means cost in this example. So I'll use k, whatever. So I've got 0.1 x cubed plus x squared plus k. Now, if my overhead or fixed cost is 2,000, then what I can do is say 2,000 is what happens when I plug in 0 here. So this is pretty easy to see that k is 2,000. So our actual cost function is that 0.1x cubed plus x squared, but then it's plus 2,000. So every now and then we'll have to translate something like this. Maybe instead of an overhead cost, we'll be told that the cost of producing 10 items is $4,000, in which case we might say something like this. And then we'd be plugging in 10 for x and setting it equal to 4,000. There's all these different options that you can have, but it's all going to be based on what your initial value is, what the point that they give you is. So that's everything we need with antiderivatives for now. Jump into the examples that are up in the text and see what you can do. If you've got any questions, let me know.